Hello everyone, welcome to this lecture on examples of countably infinite sets. So just to recap, in the last lecture we introduced the notion of countable and uncountable sets. Countable sets are those sets whose cardinality is either finite or whose cardinality is same as the set of positive integers. Okay. So the plan for this lecture is as follows. We will see several examples of countably infinite sets, and we will also discuss some properties of countable sets, specifically in the context of infinite sets. So we first prove that the Cartesian product of the set of integers is a countable set. Okay, so again, this might look very non-intuitive. You have many elements in the Cartesian product of the set of integers compared to the set of integers itself, because when I say the Cartesian product, it is going to consist of all ordered pairs of the form I comma j, where I can be any integer, j can be any integer. Okay, but what this theorem says is that the number of elements in the set z cross z is same as the number of elements in the set of positive integers. So we are going to prove that. So remember, in the last lecture we proved that whenever you want to prove that an infinite set is countable, either you give an explicit bijection between that set and a set of positive integers, or you give a well-defined sequence or a rule according to which you specify or list down the elements of the given set which you want to prove to be countably infinite, and argue that every element in that set will appear in the sequence that you are specifying. So what we will do is, to prove this theorem, we are going to show a sequence or a way to enumerate all the elements of this set z cross z. But the question is how exactly we find out one such sequence so that we do not miss any element of the set z cross z. Okay, so the idea is very clever here. What we do is, so since we are considering the set z cross z, it's nothing but the collection of all points in your two-dimensional plane, right? So imagine that you have that infinite two-dimensional plane where you have all the points belonging to the set z cross z, and our goal is basically to give a enumeration of all the points in that infinite plane such that the enumeration should be well defined and we do not miss any point in the enumeration process. So here is the enumeration process. I start with the center, namely the coordinate 0, 0, okay, which is an element of z cross z. So imagine this is your 0 cross 0, this point. Then my next point is, which I'm going to enumerate in my sequence, which I'm going to list down in my enumeration, is the point 1, 0. Okay, that means I move from my current point 1 unit to the right hand side. Then from my current point I move 1 unit in the positive direction and get the point 1, 1 and list it down. And then I traverse or go 1 unit to the left hand side from the current point, so I will get the point 0, 1. And now I can't come down, because if I come down, then I will be coming to the element 0, 0, which I have already listed down, right? Which I do not want to do. So what I am going to do is, instead of going down from 0, 1, I will continue left further to 1 unit, and due to that I will get the point -1, 1 and I will list it down. And now I will come down, because if I come down from my current point, the point which I am going to get, I have not enumerated it already. So I will get a new point, namely -1, 0, and then I continue this process. I go down further 1 unit and obtain the point -1, -1, and then I will make this whole trip again, right? So what was the trip? I started with 0, 0, go right, go up, go left, left, down, down, and then I will again make this circular rotation. So what I will do is, from my current point I will go right 1 unit, again right 1 unit, again right 1 unit, and then go up, up, and then continue this process, right? So I will be next enumerating this, then the next point, and then I will go up, then I will go up, then I will go up, then I will go up further, then I will go up further, and then continue left, right? So this is the process which I will follow. And the idea here is that if I enumerate the various points in this infinite two-dimensional place according to the procedure that I have demonstrated here, any point in this infinite two-dimensional place will eventually appear along the spiral. Okay, that's the idea here. You will not miss any point in the infinite two-dimensional plane. So that's why this is a valid enumeration of all the elements in the Cartesian product of the set of integers, which shows now that the Cartesian product of the integers or the set of all points in the infinite two-dimensional plane is a countable set. Okay. Now we will prove next whether we will see whether the set of rational numbers, which I denote by this Q notation, is countable or not. Now intuitively it might look the answer is no, because definitely rational numbers is a superset of the set of integers, right? And looks like there is no way of sequencing, because the fundamental fact about rational numbers is that you take any two rational numbers, there are infinitely many more rational numbers between the same two rational numbers. That means if I consider two rational numbers x and y, between x and y there are infinitely many rational numbers, right? So how exactly we are going to list down or sequence all possible rational numbers? So looks like that's not possible. But what we can do is we can show a very clever enumeration of the set of rational numbers, which will prove that the set of rational numbers is a countable set. Okay, and the sequencing that we are going to see here will be based on the sequencing of the elements of the point in the two-dimensional integer plane based on the spiral, based on enumerating all the points along the spiral that we had seen in the last slide. Okay, so just to recall, this was the enumeration of the set of all points, enumeration of all elements or points in the set Z cross Z, and based on this enumeration we will get an enumeration of the set of all rational numbers. Okay, so the idea is if we consider any rational number, then if it is a rational number, it will be of the form p over q, where p is some integer and q is some integer, and q will not be 0, right? So the idea is you traverse or you follow the enumeration of all the elements in the set Z cross Z, namely this enumeration here, and based on this enumeration you come up with an enumeration of the elements in the set of rational numbers as follows. If you are at a point p comma q, then you list down the rational number p comma q in your enumeration, provided q is not 0, because if q is 0, definitely that's not a rational number, and the rational number p over q is not listed earlier as per your enumeration. Else you go to the next element p comma q in the listing of Z square. That's the idea. So what I am saying is demonstrated as follows. So if I apply the rule on 0 comma 0, so if I start with 0 comma 0, so my p is 0 and q is 0, right? So my rule says that if q is 0, don't do anything, go to the next element, and my next p comma q is 1 comma 0, and again q is 0, so my rule says don't do anything. Then I go to my p comma q, which is 1 comma 1, and I will be applying the first rule here, because here q is not 0, namely q is 1, and my p over q is 1 over 1, which is the rational number 1 and which is not yet listed, right? So that's why I will list down the element 1, then I will go to the next p comma q. Q is not 0, so again I will be applying the first rule, and p over q will be 0 in this case. Then my p over q will be minus 1 over 1, which has not been listed earlier, so I will list it down. Then my next p over q is not defined because q is 0, so ignore this. Then if I go next, my p over q is minus 1 over minus 1, which is nothing but 1, and which has been already listed. So that's why I will apply the rule in the else part. Okay, so that's why I will miss this element as well. And if I continue, then when I go to the element 2 comma minus 1, it will be 2 over minus 1, which is the rational number minus 2, which has been not listed earlier, and so on. So now you can see, even though there are infinitely many rational numbers, if I follow these two rules of enumerating the rational numbers, I will not be missing any rational number, because you take any rational number, it will be of the form p over q, and it will be eventually listed down in the sequencing that I have specified here. So that means we now have a method of listing down all the elements of the set q in a well-defined fashion, and that's why this set of rational numbers will be a countable set. It has infinitely many elements, but we can count it in the sense we can sequence down, we can write down all the elements in that set. Okay, so this will be the sequencing of the elements in the set of rational numbers. Okay, now let's consider the set of binary strings of finite length. What exactly that mean? So imagine a set pi consisting of two elements, namely the elements 0 and 1. And why 0 and 1? Because I am considering binary string. So binary string will be just a string of zeros and ones. And I use this notation pi star to denote the set of all binary strings of finite length. What do I mean by that? So more formally, pi star is defined to be the union of the sets pi superscript I, where I is within parentheses, and I belongs to the set of natural numbers, namely I ranges from 0 to infinity. And what is this set pi power I within parentheses? It is the set of all possible binary strings. Okay, so I should specify here, it is the set of, okay, it is the set of all possible strings of length exactly I over the alphabet pi. And since pi consists of only symbols 0 and 1, what this pi raised to power I denotes? It denotes the set of all possible binary strings of length exactly I. So if I consider the set pi power 1, it will have only the binary strings of length 1. So it will have only two elements. If I consider the set pi power 2, it will have all binary strings of length 2. Okay, and so on. So what is this set pi star? It is the set which is obtained by taking the union of pi power 1, pi power 2, and so on, including pi power 0, and where pi power 0 denotes all possible binary strings of length 0. So we use this special notation epsilon to denote the set of to denote an empty binary string. So based on this fact, it should be now clear that each subset pi raised to power I is finite. Why it is finite? Because it has exactly 2 to the power I elements. Because pi to the power I denotes the set of all possible binary strings of length exactly I, and I can have 2 to the power I such binary strings. And if I take the union of all such sets, I get the set pi star. So it is easy to see that the set pi star is an infinite set because the number of elements is infinite. But it is the union of several subsets where each subset is finite in the sense it has finite number of elements. Okay, so now the question is this set pi star countable? Even though it has infinitely many elements, it has infinite number of binary strings, can we enumerate down all such strings in a well-defined fashion? So the answer is yes, we can prove that the set pi star is indeed countably infinite. And what we will do is, to prove this theorem, we will show a possible valid listing of the elements of pi star. And the idea is to arrange or list down all the elements of pi star according to their length, right? So we start with the length 0 strings, and length 0 string will be the empty string denoted by the special notation epsilon. Then we will go and enumerate or list down all valid strings, binary strings of length 1. Okay, and if there are multiple strings of a particular length, we arrange them according to their binary order. Okay, so for example, here we have two possible binary strings of length 1, 0 and 1, but since numerically 0 is less than 1, we will list down 0 followed by 1. Then, so basically what I am saying here is that you go to the set pi power 1 and list down the elements of the set pi power 1 in binary order. Next, go to the set pi power 2 and it will have 4 elements. List down those elements in binary order. So we have 0 listed first, followed by 1, followed by 2, followed by 3, and continue this process. Next, go to the set pi power 3, which will have 8 strings. List down those strings in binary order, and so on. Okay. So why this is a valid listing? The idea is you take any string x, any binary string x belonging to pi star. It will have finite length because as per the definition of pi star, x will be belonging to some set pi power I. We don't know what exactly is that index I. It depends upon the number of bits or number of characters in your string x, but it is a well-defined value. That means x belongs to some pi power I, and eventually after listing down all the elements in the set pi power 0 to pi power I minus 1, when we will be listing down the elements of the set pi power I, x will appear somewhere in our listing. So we will not be missing the element x. And we know that after some step, eventually the chance for x will come as per this listing to be listed down in our enumeration. So that's why this is a valid enumeration, which shows that the set pi star, even though it has infinite number of elements, it is possible to list down those elements in a well-defined way, and hence proving that the set pi star is countable. Okay. So till now we had seen several infinite sets, and magically we have proved that they have same cardinality. Now we will prove some general results about the cardinality of sets, both with respect to finite sets and infinite sets. So the first theorem is that if you have two sets A and B, and if they are countable, then their union is also countable, right? So I am not saying anything about the number of elements in the union of A and B. Of course, the number, what I am saying is that it's always possible to list down the elements of A union B. Okay. So how we are going to prove it? First of all, there might be a possibility that A and B are not disjoint, but to keep our proof simple without loss of generality, we assume that A and B are disjoint. Okay. The proof can be simply adopted for the case when A and B are not disjoint. Now we can have various cases depending upon whether A and B are countably finite or countably infinite. So the theorem statement was that A and B are countable, and the definition of countable set is that either its cardinality is finite or its cardinality is same as aleph null. So we can have three possible cases here. Case 1, when both A and B are finite, that means say the cardinality of A is m and the cardinality of B is n, then it's easy to see that the cardinality of union of A and B will be m plus n, which is a finite number, and hence A union B is also countable. Case 2 is when exactly one of the sets A and B is finite, whereas the other set is countably infinite. Okay. Now again we can have two possible cases depending upon which of the two sets is countably infinite. So what we can do is we assume without loss of generality that it's a A set which is countably infinite. That means the cardinality of A is aleph null, and the set B is countably finite. The set B is finite. That means it has exactly m number of elements, where m is some natural number. So what we are now going to show is that even in this case, the union of A and B is countable. Okay, of course, the union of A and B will have infinite number of elements because A is infinite here. But what we are going to do is we are going to show here a valid sequencing for the elements in the set A union B. So the idea here is that since A is countably infinite, it will have some valid sequencing of its elements. So let that valid sequencing be A1, A2, AN and so on. Okay. And of course we know that the set B has m number of elements. Okay. So let the elements be B1 to Bm. So what we do is we list down the elements of, we can say that we can list down the elements of A union B as follows. First, list down the elements of B set, which are finite in number, m in number, followed by the elements of the set A. Okay. Now you might be wondering why we can't do the following. Why can't we enumerate the elements of the set A first and then followed by the elements of the set B? Okay. Right. My claim is that this is not a valid sequencing of the elements in the set A union B. Why it is not valid is because since you are first listing down the elements of the set A, you don't know when you are going to return and come back and list down the elements of the set B, because that's sequencing of the elements of the set A is an infinite process and you can get stuck there forever. So you don't know when exactly you will finish that process and will come and start listing down the elements of the set B. So now what I mean here is that if I ask you, can you tell me where exactly B1 is going to appear in this sequence, you can't tell me because we don't know when exactly we will finish listing down the elements of the set A and then we will come to and list down element B1. But if I consider this sequencing which I have listed here, I know when exactly the element will appear irrespective of whether it belongs to the set A or the set B in this sequencing. If you are asking me to specify where exactly an element from the set B belongs to, I can give you that position. Whereas if you ask me where exactly is the position of an element from the A set in this sequencing, again I can tell you that okay, it will appear somewhere because as per my assumption, that element has some position in the sequencing of the elements of the set A. So that's why it is this sequencing which is valid and not this sequence. Okay. The third case is when both A and B set are infinite and countable, right? Because I am assuming my A and B sets are countable, and if A and B are both infinite, that means both the cardinality of A as well as the cardinality of B is Aleph null, and I want to show that A union B is also countable by giving you a valid sequencing for the elements in the union of A and B. So since A and B are countably infinite, they will have individual valid sequencing of the elements of the respective sets. So imagine that this is the sequencing of the elements of the set A and this is the sequencing of the elements in the set B. We want to find out a valid sequencing of the elements in A union B so that we do not miss any element in the union of A and B, and we know when exactly an element in the union of A and B is going to appear in the sequence. So a valid sequencing of the elements in union of A and B is as follows. First list down the first element in the A sequence followed by the first element in the B sequence. Then go and list down the second element of the A sequence and B sequence, and like that continue and write down or list down the nth element in the A sequence and B sequence and so on. Okay, so now you can see that you ask me any element from the belonging to the union of A and B, it will eventually appear in this sequence. It won't be the case that we get stuck infinitely for listing down that element. Whereas if I would have listed down first the elements of the A set, okay, and then list down the elements of the B set, then this is not a valid sequencing for the elements of A union B. Why? Because if you now ask me when exactly I am going to list, or when exactly I am going to see B1 in this sequencing, I don't know, because the process of listing down all the elements of the A set is a never ending process. So we don't know when exactly we will finish that process and come and write down or list or find the element B1. So that's why this is not a valid sequencing, but the same problem won't happen with the sequencing that I have specified here, namely listing down the elements of A and B sets alternatively, because it doesn't matter what is the element in the A union B, that will appear somewhere in the A sequence or in the B sequence, depending upon whether it belongs to the A set or in the B set. And accordingly, since I am listing down the elements of A set and B set alternately, it will appear somewhere in this sequence. Okay. Now, the second interesting result about the cardinality theory is what we call as the Schroeder-Bernstein theorem, which says the following. If you have two sets such that the cardinality of A is less than equal to cardinality of B, and simultaneously the cardinality of B is less than equal to the cardinality of A, then we can conclude that both the set A and B have the same cardinality. In terms of function, what we are saying here is that if A is less than equal to B, then as per the definition, we have an injective mapping, say the mapping F from the set A to B. And since B, the cardinality of the B set is less than equal to the cardinality of A set, we also have an injective function, say G, from the set B to set A. Now, if we have these two individual injective mappings, what this theorem basically tells you is that using the injective mappings F and G, you can come up with a bijective mapping between the set A and B. Okay. That's the idea behind the proof of this theorem. However, the proof is slightly involved, and due to the interest of time, I will not be going through the proof of this theorem, but this is a very important theorem which we should keep in our mind. So what this theorem basically says is, if you want to show that the cardinalities of two sets are the same, right, then one way of doing that is you show injective mappings, one injective mapping from the first set to the second set and another injective mapping from the second set to the first set. That automatically will conclude that you can have a bijection also between the two sets, and if you have a bijection between the two sets, then as per the definition of equality of two sets, they have the same cardinality. Equality of the cardinality of the two sets, they have the same cardinality. The sets A and B might be different, okay, they may have different elements, but cardinality wise they will be the same. Now the third result about the cardinality is the following. If I take any subset of a countable set, then it should be also countable. So there are two cases. The above statement is obviously true if the set A is a countably finite set. Okay, that means if the set A has say n number of elements, and if I take a subset B of the set A, of course the cardinality of B will be upper bounded by n. Okay, so this statement is obviously true. The statement is also true even if the set A is infinite but countable. So I can prove that even if the set A is infinite but countable, that means its cardinality is Aleph null, then the cardinality of any subset B of that set A is also Aleph null. We can prove that. The idea behind the proof is as follows. We can prove the theorem by contrapositive, and a simple way to understand the proof is that if the set B is not countable, that means if it is not countable, that means it is not possible at all to list down the elements of the set B. So if you don't know any method of listing down the elements of the subset B, how come it is possible to list down the elements of the superset A? Right? And that goes against the assumption that my set A is countably infinite. If I assume that my set A is countably infinite, that means I know how to list down the elements of the set A in a well-defined fashion, right? So that's a proof for this fact. Okay. So as a consequence of this statement, I can also state that if you have any set which has an uncountable subset, right, then that set is also uncountable. So what I am saying is that if you have a scenario where B is a subset of A and you don't know how to list down the elements of the set B, that means the cardinality of B is not LF null, then I can conclude that the cardinality of A is also not LF null. This is because if I don't know how to list down the elements of the set B, I don't know how to list down the elements of the set superset A as well, because while listing down the elements of the superset A, I need to list down the elements of the subset B as well, but I don't know how to list down the elements of the subset B. Okay. Now what we are now going to prove is that the set of all strings over a finite alphabet is also countable. So what do I mean by that is, just few slides back I took a binary alphabet which has only two symbols, 0 and 1, and I proved that the set pi star, which is the set of all possible strings of finite length which are binary, is countable. Now I am generalizing this result to a bigger alphabet which may have more than two symbols or two characters, right? So I am assuming that I have an alphabet pi consisting of m number of characters, s1 to sm, or m number of symbols, and pi star denotes the set of all possible strings, finite length strings, over this alphabet. Okay, so my claim is that this set pi star is countable. So again, what is pi star? The way we have defined pi star for the case of a binary alphabet, we are going to follow that definition. Pi star will be the union of various subsets pi power I, where pi power I denote the subset of all strings of length exactly I over the alphabet pi. Okay. So for instance, if my pi is consisting of alphabets say A, B and C, 3 characters, then pi power 0 of course will be the empty string. Pi power 1 will have all the strings of length 1, so I will have 3 strings. Pi power 2 will have all possible strings of length 2, so I can have strings like this. And so on. Okay. So it is easy to see that each subset pi power I is finite, okay, because each such subset will have m power I number of strings, okay, and the set pi star is the union of all such subsets, so it will have infinite number of elements. But now we want to show a valid sequencing of the elements in the set pi star. So here is how we can list down all the elements of the set pi star without missing any of them. So since the set pi power 1 is finite, it will have an enumeration of the elements of its set. So let that enumeration be this. So the first string in pi power 1 is denoted as str11. The second string is denoted by 1, 2, and so on, right? So in the subscript I have two variables. The first variable denotes the subset in which the string, so the first index here denotes the subset in which the string belongs, and the second subscript denotes the ordering of that element within that subset. Okay. In the same way, I will have a sequencing for the elements in the subset pi power 2. So you can see here each string, the first index is 2, 2, 2, denoting that each such string belonging to the second subset, and then we have the second level of indexing here, and the second level of indexing is from 1 to m square, because the subset pi power 2 will have m square number of elements. And in the same way, if I consider the subset pi power n, it will have m power n number of strings, and like that. Okay. So now what we have to do is we have to come up with a valid mechanism or valid sequencing for listing down the elements of the set pi star. and that I can do by following this sequencing, by following this ordering. What exactly is this ordering? The idea is that you first list down all strings of the form strij where the sum of the indices I and j is 2. Okay. Why we are starting with the summation of indices being 2? Because you can see that my first string here, okay, the least indexing I can have here is str11, and the summation of the indices will be 1 plus 1, namely 2. So I will start with str11. Then I will list down all the elements, all the strings where the summation of the indices will be 3, right? So that's why str12 and str21, because the summation of these two indices will be 3 and the summation of these two indices also will be 3. Now if you have many strings where the summation of their indices is the same value, then you follow the ordering depending upon then you follow the ordering among the subsets itself. So since str12 appears in the subset pi power 1 and str21 comes in as the subset pi power 2, and pi power 1 is appearing before pi power 2, that's why I have listed down str12 and then I have listed down str21. Okay. Then I will list down all strings such that the summation of the indices is 4. And again you can see here there are 3 strings. So what I have done is I have first taken the string from the set pi power 1, and then I have taken the string from the set pi power 2, and then I have taken the string from the set pi power 3, and so on. Okay. So if you can see here that if I follow this ordering, this is a well-defined ordering. Why it is well-defined ordering? Because you take any string x belonging to pi star, it will belong to some pi power I. Okay, that means it will be appearing somewhere in the listing of the elements of pi power I, and it will have a form str, say alpha comma beta. Okay, so x will be of the form say str alpha comma beta, and alpha plus beta will be some integer, right? So say alpha plus beta is say gamma. So once I have listed down all the strings where the summation of its indices is gamma minus 1, next I will be listing down all the elements, all the strings such that the summation of the indices is gamma, and during that process x will be appearing in my sequencing. So I will not be missing x, and I know definitely we will not be waiting infinitely for listing down the element x. That means we will never get stuck in this process of listing down or enumerating down the elements of the set pi star, and that's why this is a valid sequencing. Okay, so now based on the previous theory, what we can prove here is that a set of programs or a set of valid programs in any programming language is also countable. Okay, so what do I mean by that? You take pi to be the set of all keyboard characters. Okay, it's a finite alphabet because you have only finite number of keyboard characters, right? Even if you take various combinations of keyboard characters, that will give you a new character. But even if you take all such combinations, the set of all the characters which you can type using your keyboard is a finite alphabet. I am calling it pi. And we already proved that pi star is countable if pi is a finite alphabet. We just proved that because pi power I will be the set of all possible strings of length exactly I, and we know how to enumerate out all the elements, all the strings of the set pi star. Now imagine you have a programming language L. It can be C, C++, Java, Python, any programming language, and let this calligraphic P, okay, denote a set of all valid programs in your programming language. What do I mean by a valid program? I mean to say it has a start instruction or a begin instruction, and it has an end instruction, and in between the uh, between the begin and the end instruction, or the start and the end instruction, you have arbitrary number of syntactically correct instructions in that programming language. Okay, valid instructions in the sense when you compile the program, you don't get any error, you get some output. Okay, how many instructions you can have between the begin and end? Well, that can be arbitrarily large, but it will be finite, right? It won't be the case that you have infinite number of steps between the begin and the end instruction. Why that's the case? Because if you have infinite number of instructions between the begin and end instruction, how can your program be valid? How can the program will give you some output? Because to get the output from your program, you need to reach the end instruction. Your compiler need to reach the end instruction. That means after parsing all the steps between your begin and end instruction, the program has compiled and given you an output. That's possible only if the number of instructions between the begin and end instruction is a finite quantity. That means the number of steps is some natural number, positive number. Okay. So this is my set P, right? You can imagine it has many programs. But the claim is that set P is countable. Even though the number of programs is infinite, because you can keep on inserting, you can keep on taking existing programs and keep on increasing the size of the program by inserting new valid instructions in the existing valid programs, right? That way you can keep on creating new programs. This process will never stop. You can't say that after this program I can't find a new program, a new valid program, right? There is no end point there. You can always keep on coming up with new programs based on existing program. The simple thing will be just take any existing valid program and just before the end instruction insert a new valid instruction. That will give you a new program which is different from the previous program, right? And that's why this set P, which is the set of all valid programs in your programming language, is an infinite set. It's not a collection of finite number of programs. But the claim is that even though you have infinite number of programs in your programming language, that set is countable. We can list down or we can come up with an enumeration of all valid programs in your programming language. Okay. And why that's the case? Because we just proved that any subset of a countable set is countable, right? And what exactly is the set of all valid programs in your programming language? Well, that's a strict subset, a proper subset of the set pi star. Why? Because I am just considering only valid programs. I am not considering invalid programs. My set P has only those programs which will compile and will give me some output. I am not considering programs of the form which has only a begin instruction. That's all. That's also a string over the set pi star, right? This string belongs to pi star, but this is not a valid program because it has no end instruction. In the same way, the set in the string end also belongs to pi star, but it can't be considered as a valid program. But if you consider the string begin followed by end, then that's also a string belonging to pi star, but that's a valid program because you have a begin instruction and an instruction, and in between you don't have anything, but that's fine. This is a valid program. So that's why the set P will have only a subset of strings from the pi star, because pi star will have all the things that you have in the set P plus invalid programs as well, because pi star just talks about strings over the set pi. Whether that string is a valid program in your programming language or not, that's not necessary here. So that's why the set P is a strict subset of pi star. And since we know that pi star is countable, that means we know how to list down the elements of the set pi star. Using that process, we can also come up with a process of listing down all the valid programs in your programming language as well. Okay, so that proves a very interesting result, What we have proved is that even though the number of programs, the number of valid programs in any programming language is infinite, we can always list down those valid programs so that we are never going to miss any program of any valid program in your programming language in that sequencing, and it will not be an infinite process, in the sense you won't be stuck forever to find out a position of any valid program in the programming language in that sequencing. Okay, so that brings me to the end of this lecture. These are the references for today's lecture, and again I followed some of the examples from this article in the current lecture. Thank you.